First of all, Jean-Michel, it is a real pleasure to have you here with us this
You.
morning in this Chemometrically Speaking. And well, for the people, for very few people maybe that you don't know Jean-Michel, Jean-Michel, apart from being an excellent spectroscopist and expert in chemometrics, he is a wonderful person. And he is a professor at INRAE, the Institute for Agricultural Research.
Yes.
And we are really happy to have you here. So, Jean-Michel, the floor is yours.
Okay, thank you. I am also very happy to speak and to see you. Not all of you, but some. And so, yes, good morning, buenos dias, buongiorno, guten Morgen, etc., etc. Bonjour. I will speak about, yes, about increasing the robustness of chemometric models by calibration transfer, orthogonal projection, and domain adaptation. So we will make a survey of these topics, okay? And if you have any question after this presentation, and when you want, you can also send me an email. You have my email address here, so or you send the email to Jose, and he will transfer to me. Do not hesitate. Okay, so we will see. We will follow this outline. We will see what's the problem of the robustness problem, and how to manage the calibration robustness, the strategy, a bit of strategy, and then how to improve the calibration robustness thanks to three categories of methods. So first of all, hypothesis and notations. So we will assume that we have a matrix X of spectra, let's say, n spectra by p wavelengths. Could be something else than spectra, but it's more convenient to assume that these are spectra in X, and we will address the case of on a unique response. That means that we want to predict a single Y concentration, for example, and we will specifically address the highly multivariate case. That means that we have a lot of wavelengths in our spectra. And we will only address a linear modeling. That means that y hat is equal to y hat, the estimation of y here. The estimation of y is given by an inner product of the spectrum by coefficients. Okay. So what's the problem? When you have aging of devices, when you change variety of a fruit, of wheat, etc., when you change the origin of the product, the measurement conditions, the sample preparations, all these changes provoke deviations in the measured spectra. So in place of measuring X, you measure X plus delta X, okay, whatever the delta X is not a constant, okay? And delta X can be of various nature: baselines, random noise, spikes, wavelength shifts and drifts, new peaks, etc. So you have a deviation on your measurement, spectral measurement, and this delta X challenges the reproducibility of the model. And the robustness, what is called the robustness, is the reproducibility of the model with respect to this delta X. Okay? So in chemometrics, we are used to call that problem calibration transfer, because we will transfer a calibration from one condition to another one. In machine learning, this is known as domain adaptation. But in fact, we will see that it's exactly the same problem, but addressing two different domains. So we will assume in the following that we have two domains, a source domain and a target domain. Here we will name XS and YS, the source domain. We assume that this is the domain where we have done the calibration of the model, and we want to apply this model in the target domain with data which should name XT and YT. Here the T should be lower. And it could be, for example, the case of instrument standardization. You want to pass from one spectrometer to another one, or you want to transfer a model you have done in laboratory to handheld spectrometer, or drone, or remote sensing, or embedded sensors into crops, for example. So we have different levels of problem. I think if you have experience this situation of calibration transfer, you have experienced the most simple case. This is a bias. That means that your prediction, when you predict in the target domain, the model you have calibrated in the source domain, you observe a bias. That means that the model should be good apart a constant deviation here, which is called a bias. It could be also a slope, okay, or the dispersion. That means that the standard error increases, or sometimes non-linearities. So we have several levels of problems, okay? So we will see, first of all, how to manage this calibration robustness. This is a bit of strategy in order to make a series of experiments and a series of actions in order to increase this robustness. So we have developed this diagram. We have published it in 2004. And the first question to ask is, if we have G, an influence factor, that means that for passing from the source domain to the target domain, there is an influence. For example, that could be the temperature or the change of spectrometer. G is a factor, okay, could be discrete or continuous, and little g is its value, okay? So for example, if G is the temperature, G could be 10, 12, etc. If G is the spectrometer, the type of spectrometer, G could be 1, 2, the first, second, or third spectrometer. Okay, could be discrete also. So first question is G, this factor, influent? If it is not influent, no problem. Okay. If it is influent, but it's not so easy to answer this question. Okay, we have to make some experimental design and to measure and to characterize the robustness of your model. If it is influent, you have decided that it is influent, you have detected that. The second question is, can you control this factor? Because, for example, if the problem is the temperature of the spectrometer, it could be easy to put it in a fridge, in fact, to put it in an air conditioning system. If it is possible, okay. If it is not possible, the third question is, do you know the G value, little g? Do you know this value when you use the model in the target domain? That means, for example, if the problem is the temperature of the spectrometer, are you able to measure this temperature? Do you have the value of this temperature? If you have it, you can use it in order to correct directly the prediction. And you can correct the prediction in 3 ways. The first way is, which is called a priori correction. That means that you will use this value of G and the spectrum you have measured. You combine that in order to produce a new spectrum, a corrected spectrum, which will fit the condition you have in the source domain, as that means that you can input in your model without problem. This is, for example, this is example of optical standardization, which is very, very current and very usual in laboratories. That means that you have a new spectrometer, you are able to transform the spectra you have measured on the new spectrometer in order to fit the one you should have measured on the former one. We will see that after. The second way is to correct the model. That means that you will use the model you have calculated in the source domain and the G value, you combine that in order to calculate a new model which is better. And it could be, for example, local PLS. That means that depending on the condition you have, you will use a new model. We will see also that. A posteriori correction is the third way of correction, and it is very, very classical. For example, it is bias and slope correction. You apply the old model, the source model, you have an error. You can evaluate this error, could be a bias, as we have seen, or a slope, and you correct reversely in order to obtain the good value. Okay, this is what we can do if we have the G value. If we do not have the G value, it's more problematic because we have to calibrate a model which is robust over the 2 domains, okay? So here we have robust calibration or domain adaptation, and here we will see that it could be the auto-organization, web file, DIPLS, etc. We will see that at the end, okay? So first of all, A priori correction, an example, optical standardization, it is very, very used in spectrometry, and it is very old. These are very old methods. For example, you have the piecewise direct standardization here, okay? You measured standards objects. That means that you have the same object which are measured on one spectrometer and on the other one, and the source and the target spectrometer. Let's say you have standard cells of wheat. You measure them on the source spectrometer and on the target. The denomination is not source and target. It is more often master and slave, okay, but the same. So you have this set of spectra, and you simply compute a function which is able to transform the target spectra into source spectra. And you apply it on the new target measured spectra, and you apply the model. This is a forward PDS. You can also do the reverse, calculate a function which estimates the target and as a function of the source, and then you compute, you apply it on all your calibration database. There is an echo, and you apply it on all the calibration database, and you recompute a model. This is a backward application. So it's very simple. Second example is local modeling. If you want to correct the model, that means that you do not correct a priori or a posteriori, you correct the model. Let's imagine that G is the temperature of the product, okay? And we have made the model at 5 degrees, 10 degrees, 15, 20, and 25 degrees, okay? And then we have a new sample, okay, at 17 degrees, okay? So either you adopt the closest, you can say, okay, I will use the 15 degrees, it will make a small error, or you can simply also make a weighted mean of all the predictions of all the models, but weighted by a function which is will depend of the distance between the temperature you have and the temperature of the model. You can imagine here we will put a very, very low weight, here also, and here a very high weight, okay? This is an idea of correcting the model. You aggregate all the models you have at different level of a G. Okay, and a posteriori correction, bias and slope correction. Let's imagine that G is the temperature of the product, the same example that before. We have applied the model which has been calibrated on 25 degrees. We apply on 5. We observe that there is a bias and a slope, as you can see. We apply at 10, at 15, at 20, at 25, at 30, etc. And we are able to draw a relation between the temperature and the bias, and also between the temperature and the slope. Here we have these two functions. We can fit this function. And then when we have a new sample, let's say at 17 degrees, we can see that the slope will be 1.05, and here the bias will be 1.51, and we use it in order to correct the prediction of the model. This is very simple and very practical, and you can have this correction. You do not need mathematics, complex mathematics to do that. And it is what is done very simply in most of the laboratories. Okay, so now we have seen the classical methods to correct the prediction when we have the G value. Now we will focus on what to do if we do not have the G values. That means that what to do to calibrate a robust model, which should work over the 2 domains or more than 2 domains, okay? So we will be back to the problem mathematically, but very simply, it is geometry. Here, in the RP space, the spectrum we have measured is a vector here, X, okay? And B is a model, the PLS model or the linear model we have constructed. It is here, it's also a vector of the same space. When we apply the model on the spectrum, we project the spectrum on the direction of B, and then we multiply by the norm of B. It is simply the inner product, XTB, X1, B1 plus X2, B2, etc., etc. Okay? This is the estimation of your model. I have canceled the intercept because it is not useful in this reasoning. Okay? So we have that. If we add a dx, delta x here, we can see that this delta x will project also and will produce a delta y hat, a delta difference in the estimation of the y, which is equal to delta x dB. It is very simple. In fact, it is linear algebra. But if you write this expression, if you compute the absolute value of this error, you can find, this is a kind of Pythagorean relation in the triangle. You can see that the absolute value of the error is the multiplication, is the product of three terms, the norm of delta x, the norm of b, and the absolute value of the cosine between delta x and b. So in fact, it's very simple. In order to lower this expression, because we want to lower this expression, we can act on three terms. Because if we lower one of the three terms, because it's a product, you will lower the product, the result. So you can lower delta x. So it is what you do if you control G, or if you do some pre-processing or a priori correction like PDS, you eliminate the delta x. So that means that the norm is low and the product is low. Lowering the norm of B is just a recall about the importance of parsimonious modeling, because the norm of B increases with the number of latent variables. So you can see rapidly that the variable selection or the parsimony of your PLS model will be a good thing for lowering the norm of B, okay? And the third term we can act on is the cosine between delta x and b. So we can do that by two ways, either implicit orthogonalization. That means that, for example, you add some samples of the target domain in your calibration and you recalculate the PLS, and the PLS will automatically orthogonalize itself with regard to these new samples. That means that this is a kind of implicit orthogonalization. It is also the idea of red file, in which we put the difference between target and source with a 0 in front in the calibration database. And you have also the explicit orthogonalization. We will see that in detail, EPO, top, DOP, etc. And the methods of all the methods of domain adaptation in order to lower this delta x, cosine between delta x and b. Okay, we will see how to do that very simply. Okay, so if you, here is just an example to show you that the cosine between delta x and b decreases automatically if you add some samples from the target domain. Here we have, it's an experiment. We have made a PLS model on 80 apples for predicting the Brix degree, the sugar content, at 25 degrees, okay? And we have made an experimental design at high temperature, okay? So delta X is a temperature influence, okay? I can compute very simply delta X because I can make the difference between two temperatures of the same apple. The model 2 to 4, these are the PLS of computed, calibrated on these 80 apples plus some samples at different temperatures. That means that I have calibrated a new model with apples at 25 plus other apples at other temperature, at 10, 5, etc., etc. Okay, and I have added plus here I have made with 80 plus 10, 80 plus 40, and here 80 plus 60. Okay, so and I have tested these models on different temperature. Okay, so we can see normally you have 0.5. The step in a Brix prediction, Brix estimation is 0.5. Okay, here you can see we have a very high SEP, standard error of prediction, and a high bias. Okay, and the cosine between delta x and b, because I have b and delta x, I can compute, is 0.0 is 0.085, 0.85. It should appear, it can appear very low, but in fact, in this very huge space, we have 256 wavelengths, so it's a very, very huge space. Everything is orthogonal to everything, not orthogonal, but if you compute the cosine, is always, almost always very low. But what we can see, if when we add some A poles in the calibration, some of different temperature, we can see that the cosine decreases. It passes here, it is divided by 10, here divided by 3, and one more time by 3. So we pass finally from 85 to 1. So we have divided by 80. And we can see also that the shape is decreasing and the model becomes more and more robust. So it's just an experiment showing that implicitly, if you add some sample from the target domain and you recalibrate your model, you implicitly orthogonalize your model to the delta X. It is now proven mathematically. Okay, so it was just a parenthesis. So now we will see how to perform this orthogonalization explicitly with a small experiments. Okay, so this is a drawing in order to show you how works orthogonalization. Here we have two variables. Let's imagine we have only two wavelengths, okay, X1 and X2, and we have 5 samples, okay, A, B, C, D, E, corresponding to 5 levels of Y. 1, 2, 3, 4, 5. Here, everything is perfect. There is a very good proportionality. Your model is very clear. This is this line, no problem. Okay. Let's imagine that we add delta X. We add some perturbation on our spectra here. This was an example here or here, etc. And this produces new points, higher case, A, B, C, D, and E, okay, which are shifted with regard to the line. But you can observe that the direction here of delta X is always the same. It could be on the right, on the left, different lengths, but they are all in the same direction, okay? Because we are cheating, in fact. And then let's imagine that we project all these new points on a line which is orthogonal to the direction of delta X, okay? The direction of delta X, I come back here, you can see that the direction of the delta X is always the same. So we compute the orthogonal of this direction and we project these points on this new line. And you can observe that we have retrieved the proportionality. All the points are aligned and are equally distributed on the line. So we are not on the same line. We have changed the space, but we have retrieved the orthogonality. It's just a drawing in order to explain you how works the orthogonalization. And we will see now how it works in the complete space with more than 2 dimensions. So the aim of this method is to explicitly lower the cosine, okay? So the idea consists in removing from X the space which is spanned by delta X. So doing that, because B belongs to this space, if we remove the space spanned by delta X, B will be automatically orthogonal to delta X. Okay, so we just put in a G matrix a collection of influence spectra. We compute a basis of this space thanks to SVD, PCA, and we project orthogonally to this basis, and we recalibrate on this new matrix. The resulting B is orthogonal to any delta X, okay? So the mathematics seems maybe a bit complicated, this equation, but in fact it's very simple. And it is 5 lines in MATLAB. It is very, very, very simple, okay? So all this method, all the OP-based method differ in the way D is built, okay? And one parameter has to be calibrated is the dimension of P, the dimension of the space we remove by orthogonalization. So we will see different types of OP-based methods. The first one is external parameter orthogonalization. So let's imagine you have made an experimental design. you have K levels of your influence factors. Let's say, for example, the temperature, you have 10 levels of temperature, and you have L samples, for example, 8, or you have 10 or 20 apples at 10 level of temperature. And what was proposed in the EPO is to make the average of each row here and to make the difference between this average, so this mean, in order to obtain what is responsible, what is due only to temperature, not to the samples, because we have made the mean. That means that each row corresponds to the same sample, but at different temperatures. So if you make the differences between the rows, or if you mean center is exactly the same, you obtain a matrix D with K-1 influence spectra, okay? Well, otherwise, you can also just mean center by column here, because here, if you do that, you obtain more influence spectra because you make the reasoning sample by sample. You can also do that. And here, you can fill in the D matrix and use it in the algorithms. If you have not done, if you don't have done an experimental design, okay, because you have only observed same samples at different level. Let's imagine you have put a cold apple on the table and you have measured it every 10 minutes when the apple during the apple is warming up, okay, and so you have the same the spectrum of the same object at different temperature, but you do not know exactly what is this temperature, okay, you do not know, and you have not the same experiments for each sample, okay, but you know that the same sample has been recorded at different level of G, okay, you just mean center each of these samples or each of these collections, and you have influence spectra, okay, you can put it in D. So it's very simple. It's very simple. You do not need to measure the Y, you do not need to measure the G, you just need to measure the same samples at different level in different conditions. Could be the same. If you have two spectrometers, you measure the same samples on the two spectrometers. Okay. And then you make the orthogonalization. Here is the results for the problem of apples and temperature. And we can see that before EPO, we have a very, very huge bias depending on the temperature. You can see that here, each line. And after correcting with EPO, it is from the publication and for the original paper, you can see that the bias has completely disappeared and we have corrected thanks to the orthogonalization. And one point which is very important is that if you correct for this temperature, it should work for other ones. And also, if you correct for a shift of temperature, and if this shift of temperature disappears, it still works, okay? Okay, we will see that after. Okay, another method is dynamic orthogonal projection. In this method, we assume that we are unable to measure the same sample at different conditions. For example, before we have measured the same apple at different temperature, but imagine that for a reason or another one, we are not able to do that. For example, it's the case if you have made a calibration on a spectrometer and you have a new one, but the old one has disappeared, is broken, for example. So you have to transfer your calibration base on the new spectrometer, but without having the possibility to measure the same sample on the two spectrometer. It's also the case if you want to apply a model you have calibrated in 2020 and you want to apply it in 2021 on fruits or on grains, and you know that there is a shift in the spectral response between the two seasons. Okay, so here this method will answer this problem, but we assume that we have a few samples in the target domain. Here, this is the target domain. You have a few samples with the Y. Okay, we have the X and the Y. We have measured the spectrum, and you have also destroyed the sample in order to have the reference value. So if we have this, a few samples, okay, we propose to, thanks to the Y value, to retrieve the calibration set, that means in the source domain, to retrieve the spectra which best match this Y value. Okay, and we do not do that by searching, just searching. We do that by combining all the spectra of the calibration set thanks to a kernel centered on the Y values in order to have a kind of mean spectrum corresponding to each of the Y values. Okay, we have this ideal spectra derived from the calibration database, and this X hat is in fact the spectrums that should have been measured for each of the Y in the source domain conditions. Okay, so from that we are able to say that these pairs of spectra can be seen as virtual standards. In fact, it is as we have measured the same object in the source domain and in the target domain, but without having really these standards. So with these standards, we can perform a PDS, but also we can perform an orthogonalization. Okay, we can derive the influence spectra and use them in the D matrix in order to compute the orthogonalization. And here's an example we have done, because this method has been developed initially for process monitoring, in fact, because we assume that we have a calibration database, and when we put the spectrometer online for monitoring a process, we have some deviations due to the product, to the conditions, and we assume that time to time we have some control points. And the question was how to use these control points in order to make the model more robust, to increase the robustness of the model. The first idea is to say we can make a bias and slope correction, for example, but we have searched for more clever methods. Here we have the monitoring of a bioreactor, and here is the volatile fatty acid, which is a biomarker of the activity of the biomethane production, okay? And in green, we have the reference value, because we have online a sensor for making the precise evaluation of these compounds. We have made a PLS outside of this process, and when we apply this model on the process, we have the blue curve here. We can see that we start with a bias because there is something different in the process from the calibration. We start with a bias, but after a certain time, this bias disappears. Here we have some events. Here we have an event which is ammonia addition, and we can see that with this event we have a very, very huge negative bias which disappears. Here we have rinsed the reactor, and everything starts again very, very nicely. And here a second event of ammonia addition with a very, very dramatic negative bias on the blue raw PLS model. When we use only these 2 points, 1 and 2, in order to compute the top, we can see that the first point we use is able to correct for the bias very efficiently. But here there is a deviation, a small deviation. When we use a second point at this event, we can see that we can reestablish the robustness of the model, even for this event, which is very, very strong. We have a small deviation, but very, very lower than the deviation of the raw PLS model. So this is an example of how to use DOP for process monitoring. Okay, so as a summary of orthogonalization-based methods, there is other orthogonalization-based methods like TOP, EROS, etc. So there is some pros and some cons. So the pros is that the model becomes independent from delta X. It's very important. That means that the model still works if delta X disappears, okay? That means that we can see that here, we have corrected here, okay? If we had corrected with the bias and slope, here we should have a prediction very, very higher. Here with the orthogonalization, we have established a model which still works if the delta X disappears. The correction is embedded into the model. That means that there is no need to apply the projection before applying the model in the target domain. The model is orthogonalized, so it becomes robust regarding the D matrix, the delta X you have inputted in the D matrix. Several influences could be managed. You just have to put all the influences you want to correct for in the G matrix and to process. And loadings P are meaningful. That means that if once you have calculated with the G matrix, you have made your PCA, you can examine in order to make a diagnosis of what happens on your spectrometer. But there is some cons. Some extra knowledge is needed to build the G matrix always, either some standards or some Y value in the target domain. One parameter has to be tuned. This is the dimension of the P matrix. I told you that, and I did not explain how to do that, but there are some methods. And also, which is something which could be very difficult for some practitioners, is that you have to rebuild the calibration. That means that once you have done the orthogonalization, you have to redo the PLS with all the optimization steps, etc., which could be difficult, in fact. For chemometrician, it appears like something very basic, but in fact, it could be difficult. Sometimes it's really it's much easier to do a bias and slope correction without mathematics than doing a new PLS, in fact. Okay. So now we will see some, I think I am on time, yes. Other methods from machine learning. We have seen some methods from chemometrics. We will see some other methods from machine learning. So calibration transfer is in fact an issue also in machine learning. It is known, it is called differently. It is called transfer learning, domain adaptation, or multitask learning. And among others, some have been made for or tested on spectra. Okay, for example, there is a transfer component analysis, or DI-PLS, domain invariant PLS, or spectral space transformation. Okay, we have the references here, and we will see these methods. And in fact, actually, orthogonal OP method, orthogonalization method, can be seen as DA methods, because we are with the orthogonalization, we are just searching for something which is common between the two domains. Okay. So first of all, the transfer component analysis. So as the idea is to search for components, spectral components, which are common to both the source and target domain and are predictive of Y. Okay, if we remove this condition, it's very easy. Huh? You multiply by 0, it's okay. So we search something which is predictive of Y and common between Xs and Xt. Okay, the algorithm is to reason on the distribution of spectra and the distribution of Y, and the conditional distribution of spectra regarding the Y. So if you consider these two distributions, okay, distributions, that means that all the spectra you can collect in your domain, in your application, we compute, the aim is to compute a function phi, so that the probability, the distribution of phi of xs is equal to the distribution of phi of xt, because at the beginning, if we have a problem, a domain transfer problem, that means that the two distributions are different, okay? But restricting this phi function to the fact that the probability, the conditional probability of xs regarding ys and xt regarding yt are also equal, okay? So I do not give the details of the calculation, but it is done thanks to the kernel tricks, some kernel tricks, because there is a metric for assessing the similarity of distribution, which is based on kernels, and the common components are extracted from an eigenvalue expression, which is very nice for chemometrics, in fact. So this was the TCA. Another method is domain invariant PLS. So the idea of DI-PLS is to constrain the latent variable building to be domain invariant. So I think that if you are used with chemometrics, you know the NIPALS algorithms. The NIPALS algorithms aims to minimize this quantity. We are searching at each step of the NIPALS for each latent variable of the PLS. We search for weight, W, in order to minimize this quantity, X minus YW transpose. Okay, this is the norm of that. This is the error, in fact, of prediction. Okay, And the DIPLS modifies the determination of Y by adding a penalization term with a lambda here regarding this inner product. And this inner product is, in fact, the product of W is a projection of W on the difference between the two covariants of XS and XT. Okay, we calculate the covariance of XS, the covariance of XT, we make the difference, and we express that difference as this expression with a diagonal matrix with sigma 1, sigma 2, sigma k, and we compute this matrix delta, and we input this matrix in this inner product. Briefly, that means that we will search W, which is orthogonal to the difference between the two domains, in fact. Okay, because this, if we lower this expression, because we will lower the sum, we will lower this expression, that means that we will lower the cosine, as we have done with orthogonal projection, but it is written differently here. And lambda is a regularization parameter. Okay, this is the IPLS. Okay, here we will see a comparison between TCA and DOP, okay, because in DOP is also a transfer domain adaptation methods. In fact, here, so I have to read with myself, excuse me. So we have two instruments, okay, in green and red. And here on A, we have PLSR calibrated on source and tested on target. This is the problem we have, in fact. On B, this is the prediction after DOP calibrated on source and tested on target. So it means that we have applied DOP between the two domains. And C, we have the TCA. We have applied TCA in order to make the calibration transfer. So we can see that TCA performs worse than DOP, but it's not very fair. The comparison is not fair because in DOP we use the Y, some Y's of the target domain. In TCA we do not use, okay? Not explicitly as DOP is doing, okay? So here we can see the score plots of the PLS, okay, LV1 and V2. Here we can see the problem. We can see there is a big shift between the two domains. With DOP, we can see that this shift has disappeared, and also with TCA, but in another manner, okay? Here on the right, it is the same, but it is for another data set. Here was for two spectrometers, and here it was, if I remember well, yes, it's a problem of temperature. We have two temperatures in the prediction, and we can see similar results. Okay, it is taken from this publication, this paper here. Okay. Another example, because TCA does not use the Y, we can assume that if we have a shift in the Y between source and target, that could state a problem. Here we have tested, in fact, we have for we have two seasons. Season 1, we have taken all the Y values, it is dry matter. And in season 2, we have used only the left part of the histogram for the dry matter. And we have tested the transfer between the two domains. And we can see, as expected, that DOP performs better because we use the Y. And TCA does not perform very well because there is a difference in the Y. This is just to illustrate that in TCA, and also it could be the same in other domain transfer method, we assume that we have the same distribution of Y between the two domains. It's very important. Okay. Another method is spectral space transformation, SST, and the idea is to use standards to transform the spectral space. So, in fact, the same idea as PDS, but using covariance differences. You remember in PDS, we use the differences, we use the two standard sets in order to compute a function which transforms the spectra from source to target or from target to source, okay, explicitly. Here, we will not use the spectra of the standard, but the covariances of this set of standards, the covariance build covariance calculated in the source domain and covariance calculated in the target domain. That means that the spectral space transformation aims at aligning the shape of your cloud, the shape of your spectral space into the two domain, because this shape is modeled by the covariance matrices. So we have X1, X2 standard sample in source and target domains. That means you have measured the same sample in the two domains, okay? And we make a decomposition, SVD, standard value decomposition of X1, of X2 also, and we use this decomposition in order to correct any new X we measure. So it's a kind of linear adjustment. In fact, you can see here that we use the inverse of P2 multiplied by P1 plus here minus P2 multiplied by P2. It's a kind of linear adjustment, in fact, but using the covariance matrices. Okay, this has been published in 2011 by Chinese researchers. Another method is unsupervised dope. It has been done by Valeria Fonseca-Diaz when she was here in Montpellier. The question was, okay, dope functions very well, works well, but how to do more or less the same, but without the Y value in the target domain. It's really a challenge because all is done with this Y value. As you remember, with this Y value, we compute the ideal spectra we should have measured in the source domain corresponding to the Y. So, how to implement DOP without this Y? And so to merge advantages of the UP method and DA methods, because the DA methods do not need the Y. So, and the specific question, how to build the delta X using the covariance matching paradigm. So that means that we will, as SST, we will assume that if we are able to find a space or to find a space where the covariance matrices of source and domain samples are the same, the problem will be solved. Okay, so the algorithm is very simple. We make a SVD in the source domain. We make a SVD in the target domain of the standards, and we write that, in fact, this decomposition is the same as this one because this is a projection, in fact. And the idea of Valeria was to combine the two domains, VS and VT, in this operation, in fact. In place of reconstructing the XT by this operation, she mixes the two domains by mixing the two covariance matrices. And she computes the D matrix by the differences between the true spectra we have measured and the ideal spectra we should have if we reconstruct with the source domain. This is the idea. And then the D is used in EPO classically. Okay. And she has proved also, Valeria, that there is a link between UDOP and SST. So I will not enter into details, but here you can see that finally, if we write the SST equation, we can exactly obtain the same, not more the same, but something which is very similar to UDOP, in fact. So finally, there is a justification, a theoretical justification of UDOP regarding the SST. So UDOP, in fact, is an unsupervised standard-free alternative to SST because SST, I recall you, uses set of standards. Okay, so it's very nice results, and we have applied here. We add two sets of spectra, here source and domain. The source was rice, the spectra of rice in kernel form, kernel shapes, rice, a kernel of rice, okay, kernels of rice. And the target was the powder of rice, of the same rice, okay? So you can imagine that spectrally speaking, not chemometrically speaking, but spectrally speaking, the shape is completely different because the particle size is completely different. So the challenge was to pass from one domain to the other one, thanks to UDOP. The second example is 2 seasons of spectra of peers harvested on 2 seasons, season 1 and versus season 2. Okay, and you can see here that the 2 mean spectra are very different, and for the rice, much more. Okay, so we'll see the results. So for the rice, this is the original model on source. So just to show what is the performances we are expecting. We are expecting 0.5, let's say, as a RMSEP. If we apply the original model calibrated on the source on the target, we can see we have a big slope, and we have the SEP is increased, is more or less the double of the original one. Okay. If we compute DOP and we apply on the source, we can see that we are able to retrieve the same result, but with less latent variable, which is classical. And when we apply on the target, we can see that it corrects, but there is a little slope. But the RMSEP is not so much, it's 0.5 in place on 0.45, in fact, 0.51 in place of 0.45. So DOP works it's not so spectacular, but it works. Okay, so we are able to correct. That means that if we find the good transformation, we are able to correct between the 2 domains. If we apply top, that means that we assume to have the standards in the 2 domains, that means that we make an EPO between the two set of standards. We can see also we are able to correct and to retrieve something which is better than the source domain. So that means that this is applied on source. If we apply on target, it does not work so good, so well. And UDOP, finally, if we compute UDOP, we can see that we have more or less a bit lower, but more or less the same results at DOP. Okay, so that means that the principle of UDOP is validated on this application. I recall you that this application is a challenge because we want to predict powder of rice from a model which has been calibrated on kernels of rice. So it's a very, very difficult. So it's not so bad. Okay, it was encouraging. And on peers, more or less the same, that we can see here that UDOP is performing better than DOP. Okay, and so that means that we have very, very encouraging results with UDOP. Okay. And here we have some drawing just to show the effect of UDOP. If we have no orthogonalization, if we make a PCA on the 2 sets of spectra, here we have made a PCA. This is for the rice, and here it is for the peers, I think. Yes. Here, these are the mean spectrum. These are the loadings. No, these are the loadings. No, it's not done on the complete. This is a PCA computed on the source and a PCA computed on the target. This is a superimposition of the 2 loadings. We can see that the domains are completely different because the loading of the PCA computed on each domain are very different. And after applying UDOP, we can see that after one component, the mean spectra are aligned better, and after 2 components, they are completely aligned. And the same, more or less the same for the peers. Okay. And what is very important is that the shape of the spectra is not completely changed, as we can observe sometimes with the EPO or other orthogonalization methods. That means that here, for example, for the rice, we retrieve the peaks, the typical peaks we have on the source or target domain. I don't know exactly, in fact. Okay. Okay. So we arrive at the conclusion. I think I am on time. So calibration transfer and maintenance is a widely studied issue. In fact, there is a lot of problems to solve, a lot of methods. for a lot of situations. I think I have shown you a lot of different situations and a lot of different methods. We have some methods for machine learning that could be adapted to chemometrics, and it's very important because in machine learning, but it's, for example, in deep learning, there is a very new, not very new, but there is a trend which consists in learning networks for processing spectra or images, processing data without any goal, just the goal to reconstruct the data. For example, you put a lot of spectra without the why, and you train a neural network in order to analyze this spectra, but without a particular aim, just the aim of analyzing this spectra in order to detect the peaks and the slopes, etc., etc. And once you have trained this network, you specialize it on a particular problem, for example, for predicting sugar content in apple or for predicting moisture in wheat, etc., just with a few samples by doing this domain adaptation. And it is known as transfer learning in the neural network paradigm, but in fact, it's exactly the same as a calibration transfer in chemometrics. And we can imagine, for example, in chemometrics, to have a lot of data, spectral data, and we have this data. Let's imagine a spectrometer on a line, or if imagine that you are processing the spectra coming from satellites, and you have a lot of spectra. You can imagine that doing something like a PCA in order to train a model to analyze this spectra, and then to transfer this model regarding a specific problem. This is very new paradigm, a new ideas in chemometrics, okay? And this idea comes from machine learning. And there is still some space for innovations. We can have new methods every day, in fact, and the grail is not still fun, so we have some work to achieve now, and we have some nice days to live. Okay, so thank you for your attention.
Oh, thank you very much. It was really interesting, and I can actually predict the eyes of a German Basque person in the audience that are like this right now, especially from this last part. So thank you very much. It was fantastic, as usual. Do you have questions? You can just write in the chat or open your cameras and your microphones, whatever you consider.
Okay, Andreas.
I have to say something. Okay. Yeah, I have one question. If you have deviations from one setup to the next or from one situation to the next, so introducing mostly systematic errors, yeah. So how which can be calibrated, as we know, yeah, by different methods. You showed 3 pathways how to do this. This has to do with accuracy. So at the end, what happens if the precision is also affected at the same time? And for example, if statistical errors in comparison with systematic errors are even large, so there might be large statistical errors. How can this be handled, or can you distinguish between, because normally they cannot be calibrated, yeah, but it can appear as a kind of drift or shift if the statistical errors are large.
Okay, so if I have well understood, that means that you have this kind of block effects, systematic effects, and you have added to these effects some other errors, in fact, some other, yes. So it depends. All the methods I have presented, in fact, orthogonal projection, etc., are based on the assumptions that these spectral shifts, spectral differences are not aligned, not too much aligned with the Y, with the net analytic signal, what we call the net analytic signal. That is the part of the spectrum which is directly related to the Y. Okay, this is a B, in fact. Okay, If your perturbation is aligned with the B, you are dead. Because you cannot make the difference between a delta Y and delta X. In fact, it's a completely. But fortunately, we are in spaces of so huge dimension. This method functions only for spectra. In fact, if you want to apply with, for example, 4 and 5 wavelengths, it's more or less impossible to do, because first you consume each time a dimension. That means that you remove a variable each time, a rank, okay? So if you are in a spectral with a 500 wavelengths, you can consume dimensions. It's not a problem, because your real dimension is maybe 20 or something like that. So you can do that. So this is the first assumption. And the second assumption is that there is no alignment of Y and delta X, of delta Y and delta X. But fortunately, in these spaces, it's often the case. This is often the case.
Yeah. Do you see a difference when if you have information for calibrating, then it's easy. If you don't have, you have to play with some regularization or whatsoever. And if you, for example, use the support vector machines and a high dimensional hyperplane, that might also correct this in a similar way, or is there a difference in performance?
No. I think it could be if you have the data. That means that with the SVM or other of neural network, for example, if you put in the neural network or in the SVM with this high dimensional, infinite dimensional space, and you are able to draw the limits, etc., yes, it will work. But you need to feed your model with data from the source and the target. Okay. And if you have many targets, let's imagine you have a network of spectrometers, if you have to feed with data from each of these spectrometers. So it could become very, very time consuming. This is why we have we propose some tricks in order to correct with a few samples, or either no samples at all, but no, just spectral, let's say, not reference values. Okay.
Okay, thank you very much.
You're welcome, Andreas.
Well, actually, I have many questions, and I would love to start working on these issues, because actually for me, the change in the paradigm that comes from the classic chemometrics is that you have a device, you have another device, you need to put this device together. But then the change of the paradigm is that, well, you can think that you have one batch today, you have one batch tomorrow, and the day after tomorrow, and there are drifts. So it's actually something similar, and you have one device, second device, and you have to put all together. This is also kind of applied for, I'm imagining, harvesting, but the examples you put there, you measure 1 year, next year nature changes, so, and your device changes, so you have to also put these together. And there was a question when you put the very last example, when you explained DOP, I was imagining, what is the likelihood of overfitting? For instance, if you have the information of 2 years, and then you want to add a third year, so you build the model in GR2 with the data of year 1, year 2. So what is the likelihood of overfitting these two compared to the third one that will arrive the third year? So how do you manage this? How do you see this overfitting, if it is overfitting?
Yes. So, yes. If you're right. In fact, there is two categories of methods. The first category is implicit orthogonalization, implicit regularization, let's say. That means, for example, you put samples from year 1 and year 2, and you increase your model, you search for details. As Andreas said, you can also use SVM, what you want in infinite dimensional space, etc. In this case, there is a risk of overfitting, because you search a model which fits both conditions. Okay. In orthogonal, when you use orthogonal projection, in fact, you remove things. That means you search to remove the differences. Okay. And doing that, you cannot overfit. You can just degrade your model. You can just kill your model. But if you do that, you see that you are killing your model. Okay. You can, because the problem of overfitting is that you think that you have a good model because you have made some statistics, etc. But in fact, it's not true because you have done an overfitting, but you cannot see. But if you remove detrimental information, the only risk you have is to destroy your model. But you see it directly because your SIP, your SEP, your SSEV drops down, and you can see that no, I cannot do the if you cannot do the orthogonal projection, that means that your perturbation is aligned with your Y, in fact. Okay, there is no linear, there is no subspace including the delta X. Okay, it can appear. We have seen that on the soil, on the spectroscopy on soils, and we didn't succeed in applying orthogonal projection. In fact, no, okay.
Because and there is another question that is somehow related, that it goes with the second part, the part, well, the second part, the last part you explained, in which you have some data. There are methods to create or predict data from that data. That is, you have some spectra, you predict new spectra that you can use then to reinforce the prediction ability of your model. So for me, it's always a little bit obscure how you can do that, because when you have, imagine 2 classes, right? And you have 10 spectra per class. Then with these 10 spectra, you can create more data related to that spectra. That say you want to create 50 spectra more of that class in order to reinforce the thing. My main question is, how can we explain areas or zones in our space of those classes that are actually not included in this spectra, in these 10 spectra that we have measured? Can you more or less understand what I mean?
In fact, all the paradigm of this method is based on the covariance matrices. And if you are able, you have 2 domains. If you are able to have a good image of the covariance matrices, first you can say, oh, because the covariance matrices are different, I have a problem. Okay, and the idea of this method is to find something either by removing or by transforming the spaces in order to align these covariance matrices. And all the paradigm is based on that. Okay, and you can do that thanks to samples, some few or many samples, depending on the methods. But all the trick, all the problem is to compute these covariance matrices and to transform the spectra in order to align these covariance matrices. Okay, and in fact, depending on the problem, but very, very often on spectroscopic applications, the chemical rank of your problem is not so high. In fact, you have maybe 10, 15 latent variables. So in fact, that means that you can solve the problem with a few objects, with a few spectra in order to compute. But well chosen is better. not the okay. Well chosen spectra, well chosen objects can give you a good idea of your covariance matrix. Okay, and 2 covariance matrices, and how to align them and how to correct them, etc. Is always around the same principle, always.
I would love to. I think Andreas will agree with me that we would love to elaborate a little bit more on this, because that's something really interesting. Is there any question in the audience? No? Well, so then let me just stop recording first. Here we are. And